Welcome to our unit on circles. Okay, so this unit's going to cover all of Chapter 10 and a little bit of Chapter 11, which goes into a few more properties for circles that we're going to need to know. Okay, so we're going to start with Section 10.1, which is properties of tangents. And our big idea will be we'll be able to identify the different parts of circles and also calculate some of the lengths that are associated with those circles. Now, one thing I do want to mention here is that the tangent we were talking about when we looked at right triangles is going to be different in some ways than what we're talking about here, since we're referring to an actual length, okay, or segment or line. So similar in some ways, but different for what we're going to talk about today. Okay, so go ahead and start by copying down these definitions. I'm going to show them one at a time, and if you need to pause the video to have more time to copy, feel free, but I'm going to go through them rather quickly. Some of these you may already know, but let's start with the definition of a circle. Circle is the set of all points in a plane that are equidistant from a single point. This point is called the center of a circle. Now, we do use some symbol notation here. If you draw a circle with a dot in the center and then put a letter next to it, we are identifying the center point, and that's the name for the circle. Okay, so circle P would be the name if we saw this symbol. All right, and now I'm going to reveal a diagram over here on the right to help us with the rest of these vocabulary terms. So radius is a segment with endpoints at the center of the circle and any point on the circle. Okay, so must start at the center, but it can hit any point on the circle. A chord is a segment with both endpoints on the circle, as shown in green in the diagram. And finally, a diameter is a chord that passes through the center of the circle. So it has to connect on its endpoints, both sides of the circle, but also diameter has that one extra piece of it must go through the center. Now, one thing in terms of lengths that we know is that the radius is always half of the diameter. Radius equals half the diameter. Okay, vice versa. The diameter is twice as long as the radius. So that's going to help us determine some lengths in a circle as we go through. Okay, so a couple more definitions. As we see in the diagram, we have this line called a secant. And this is a line that intersects the circle at two different points. Okay, so you can see our green line up at the top is intersecting our circle in two locations, here and here. All right, a tangent, and this is the one we're going to talk a little bit more about in a few slides, is a line in the same plane as the circle that intersects the circle at a single point, which we refer to as the point of tangency. So that one is marked for you in red at point B on the diagram. So tangent can only intersect the circle once. A secant has to intersect it twice. Okay, so here's a quick example. Go ahead and pause the video and try to answer these three questions. Okay, so for A, when we're looking for the radius of circle A, we have to count the distance from the center to any point on the outside of the circle. So that's going to be a radius length of 3. Okay, so when it asks you for the radius, it's asking you for the length. Okay, in question B, find the point of tangency of circles A and B. So point of tangency is the point where they intersect, which would be located right here. And that point is at 6, 3. All right, question C, the point of tangency for circles C and D. Notice that D is inside of circle C, but they still only intersect in one location, which is way out here at this point. Okay, so that point is located at 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 0. Okay, any questions on these? You can bring that with you to class, but let's keep going. So the next topic we're going to talk about are coplanar circles. So coplanar circles can intersect at 2 points, 1 point, or no point. So here are our different types. we see two intersection points can happen, the two circles on the top. Okay, one intersection point. Those would be tangent circles, just like in the last example. Okay, so we can have a tangent where the circles are next to each other, or a tangent where one is inside of the other. Okay, circles don't have to intersect, so no intersection has two different variations. One of them is when they have different centers. Okay, so the center of the circle on the left and the center of the circle on the right are not the same, but these circles also don't have any points of intersection. Different from that is the example below. They have no intersection, but the same center, so they're both starting at the same location, one of them inside the other. We refer to these as concentric circles. Now, there is a third option where I didn't show this one, but for no intersection, they can still have different centers, and one of them can be inside of the other. So, for example, if I have a circle here and then a smaller circle inside of that, they do have different centers, but it doesn't have to be that they're outside of each other. Okay, next term we have is called a common tangent. So this is a line array or a segment that is tangent to two coplanar circles. Okay, I've drawn two examples for you here. So on the left, we see the red line is intersecting the smaller circle at one point right here and the larger circle at one point right here. Okay, in the example on the right, we have a point of intersection on each circle. Now these actually have slightly more specific names. On the left, we would call this an internal tangent. Okay, the reason we call it internal is because if I drew a line connecting the two centers of the circles together, so I create this segment, an internal tangent will intersect that segment connecting the centers. In the example on the right, I have what's called an external tangent. So for this one, if I do the same thing where I put the centers in and I connect those together, notice now that my external tangent does not intersect that segment created. Okay, so this is the difference between the two names, internal and external, but both of them are referred to as common tangents. Okay, so I'm not going to show you the answers to this one, but I want you to pause the video and take a second and see if you can draw all of the common tangents for each pair of circles. Okay, so depending on how they intersect or don't intersect, some of them have more than one common tangent. So see if you can find all of them, and we'll talk about how many each pair of circles has in the next class. Okay, so we have two theorems in this section. Pause the video and take a minute to copy them down. For this first one, theorem 10.1, if you have a line that's tangent to a circle, it's going to be perpendicular to the radius of the circle at its endpoint. So in the diagram, we see line M, which is in blue, is perpendicular to the radius that meets at the point of tangency, point P. And that will always be true. Okay, tangent lines have to end up perpendicular to the radius when they're drawn to that point of tangency. Okay, second theorem that we have in this section, 10.2, again, pause the video to copy it down. But if we have tangent segments that both come from the same point outside of the circle, we call them external points, those tangents are going to be congruent. Okay, if you look at the diagram, I have tangent SR and tangent ST. Now both of those started at point S, and because of that, it makes them the same exact length. Okay, so SR and ST would be congruent. Okay, I'm going to do two examples with you, and that'll be it for the notes here, and then we'll try some more in class. The top example, RS is a tangent to circle C at point S, and RT is also a tangent to circle C at point T, and we're going to determine the value of x. Well, if you remember theorem 10.2 that we just looked at, because these two tangents are starting at point R, they are going to be congruent, same length. So RS is going to be congruent to RT. Because that's true, I now know that I can take those two values and set them equal. So 28 equals 3x plus 4, and now I can solve for x. 24 equals 3x, divide by 3, and then I get that x is going to equal 8. All right, so when you have those two tangents starting at the same point, keep in mind that you can set those values equal. Okay, using that same understanding, let's answer the second one. So go ahead and try this first. All right, hopefully you started this one by recognizing that since we have those two right angle symbols in the diagram, that the two outer segments are tangents. And they're both coming from the same point, so they're going to be congruent. Okay, so that means I can set them equal. X squared equals 9. So I need to solve for x by taking the square root. So I'm going to get x equals, now how many of you answered 3? If you did, you've got half of this one right. But this one actually has 2 answers. See in the question it says, find the values. If I look at both the positive and negative 3 values, when I square those numbers, I get 9. So 3 squared equals 9. And negative 3 squared equals 9, which means that this has 2 answers. X can be either 3 or negative 3, and we write that by using a plus minus symbol, which I have right in front here. Okay, meaning both positive and negative answers work. All right, so I'm going to show you these last 2 examples, but I'm not going to do them here. Copy them down. We're going to start with these in class, and you're welcome to give them a try, but they do have a slightly more difficult approach in terms of how to solve them. So think about what you might be able to label in the diagram or how you might use the information to come up with a way to answer the question, but bring this with you in class. We'll start here. All right, also, bring all of your notes and any questions you have with you, and I'll answer anything that you didn't quite understand or if you want another look at. See you in the next class.